Okay. Recording now. So today's lecture is going to be on the short side because I think the most of what we're going to talk about today is going to be review, this is what we talked about this semester or these past 8 weeks, and just so you can get a bigger overview of what was discussed. But we didn't exactly finish off last lecture, so I'm going to start here. And I've got the next 2 slides here, actually 3 slides. I've got some notable examples of excellent lightweight design in automotive. The first one I've talked about a little bit already, the Lotus Elite. This was a car that was made from like 3 large fiberglass shells that were made at Bristol Aircraft back in the 50s. And the car had this is I think the closest anyone's ever come to a true monocoque design for a car, at least for a passenger car. And these big pieces of fiberglass had some inserts in them for taking point loads. So where the suspension would feed in, or the engine mounted, or the windshield attached. Another interesting design I've also discussed a lot is the Maserati Tipo 61. This is the so-called birdcage Maserati. This might be the closest anyone had ever come to making a full space frame. And the car was made up of all these sort of tiny little tubes that were welded together to make a very intricate space frame. It's called a birdcage Maserati because there were so many tubes that if a bird got trapped inside, it might not find its way out. The Lotus 25 was an incredible breakthrough, I think. 1962, this is the first aluminum monocoque in Formula One. Then the Lotus 49 was the first time anybody used an engine as a stress member in Formula One. Equally as impactful vehicle. And moving to the next slide here. Okay, I discussed this last time too. The Porsche 917 space frame design, aluminum tubes, very, 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 very fragile, very lightweight car with I think a flat 16 engine, lots of like 1,000 horsepower, but very low chassis rigidity, but beautiful to look at nonetheless. The McLaren MP4-1 from 1981. This was the first carbon fiber monocoque anybody ever made in Formula One. This technology of using carbon fiber as the primary structure with this sort of tub structure in the middle where the engine is bolted to the back and the front suspension is bolted directly to the front of the monocoque. This was the first time I ever did this, and this design has become pretty much standard technique now in Formula One. Every Formula One car out there is pretty much built like this now. The Porsche 962 from 1983. This car was a very successful racing car made from aluminum skins that were riveted together. I don't know if there's any adhesive in there or not, but there might have been. There's a steel rollover structure, but the primary load handling capability for the suspension mounts, for example, which is where the most load feeds into the structure, was made out of aluminum. One of my favorite street cars here, the Lotus Elise, very fragile little car, but conceptually very interesting in that it used these large aluminum extrusions that were bonded together rather than welded. We talked about this, I think, in lecture number 2. The big significance here is that rather than welding, they bonded the tubes together, and the advantage there again was that because they didn't create a heat affected zone from welding, there was no drop off in the strength of the material around the weld. This meant that they could continue having a thin wall extrusion through the whole part rather than having to beef up the whole part and make it thicker in order to compensate for the heat affected zone. So the vehicle came out to be quite light. The original lease was around 1,600 pounds. I don't know how much you guys are into cars, but that's incredibly light. Most cars right now on the street are sort of pushing close to 4,000 pounds, like 37, 38, 4,100 pounds, really, really heavy. But this car was amazingly light. Okay, the BMW Z8, another vehicle made out of extrusions. It was welded together. The vehicle wasn't all that light, but I included it here because it had some very efficient load paths. The way that the design was so that the any kind of impact load, for example, a bending load, would flow very cleanly into the aft portion of the structure. So you see it's got these front rails. They nicely bifurcate into an inner rail and an outer rail. And then everything is very shock tower centric, and that you've got these load paths going right here, this diagonal going to the shock tower. Very, very clean design. I don't know that the real vehicle was all that light, but it was a clean, nice, clean way to do it. The Porsche Carrera GT, this was, I think, a first time I've ever seen sort of this mid-spectrum concept designed into a car where there was sort of a structure that was more like a bicycle frame, where you had something that was kind of like a space frame, but not quite because the tubes are under bending or the structural members are under bending, but you didn't have a fully shell design, a full stress shell design like you do like an egg or an airplane fuselage. And you had these, these sort of tubular, quasi-tubular structures, or semi, I call them mid-spectrum, as you see here. The 2006 Porsche Cayman. Porsche actually has done some very nice clean designs when it comes to structural optimization with rails and rails feeding into rocker panels and tunnel structures. And this is also a multi-material structure. So they use steel for the primary load pass, and then they use aluminum for the closure panels. They probably could, they probably could get away with using aluminum in some other places too and have a similarly stiff structure. Someone raised their hand. Gabriel, what's up?
Yeah, is I guess the cabin section of the Porsche Carrera GT, is that like a carbon monocoque, it looks like?
Which one, the Carrera GT or the Cayman?
The Carrera GT.
Yeah, that's exactly right. This area in here is a carbon fiber monocoque, just like any of the race cars I pointed out. You've got the center cell. They didn't use the engine as a stress member. Okay, there's a good reason for that. Gasoline engines make a lot of vibration, as you know, right? Even a V8, which is theoretically perfectly balanced, there's still a lot of vibration. And if you bolt that hard to the primary structure, it's going to go right into the driver. The driver's not going to like that. It's going to be really, really horrible. There was a Ferrari, the F50, where they bolted the engine in as a structural member. And the F50 was never a big success. A lot of customers complained because there was so much vibration coming up. So it's really hard to do that on a passenger car. The prospects of electric vehicles, I think, are a real game changer here, because that vibration problem goes away, right? So now you can start to think about, can I use the engine, or the motor as it is, as a structural member? Can I use the casing for the motor as a structural member? And then the battery, right? I mean, the battery is really where the weight is when it comes to electric vehicles. It's not the motor, it's the battery. And as we discussed, I think in lecture 4, this is already moving forward. There's electric cars out there, or Tesla's planning electric cars, where the battery will be used as a primary structure. So, and then I also presented a scooter, I think, in the last lecture that showed, you can use the battery box as a primary load path, and it's very effective at reducing weight. So this Porsche, they weren't able to do that because I got a big gasoline engine, so they built this sort of tubular structure around the engine that, like I said, I call it mid-spectrum. It's not a monocoque, it's not a space frame, it's somewhere between. That might actually be the latest solution, having this sort of semi space frame carbon fiber monocoque where you don't have a fully stressed skin like this. You can very well imagine a structure like the back of this Carrera GT making up the rest of the vehicle as well, and then using something very thin and light to close out the gaps so you don't get wind and water in the cabin. Yeah, I think there's a lot to be had. I think quite honestly, like when you have a full monocoque, even in Formula One, you probably have a lot of superfluous material, and you probably could go lighter. I have a friend who used to be a composites engineer at McLaren, and in the Formula One program, and he used to tell me that the drivers demanded that the torsional rigidity of the vehicle be much stiffer than anything you've ever felt on the road. So, some of the stiffest body structures in torsion are like the Porsche Cayman, which is has a torsional stiffness of around 40,000 Newton meters per degree. Okay, the Formula One cars that he was building were up around 60 or 70,000 Newton meters per degree. That's most cars out there, most your Toyota Camrys and Honda Civics and stuff like that, they're sort of in the 20 to 25,000 Newton meters per degree, and then these big SUVs out there, they're even much lower than that. So the level of torsional rigidity that these Formula One cars are able to achieve is so high. But you don't really need to go that high I think, to have a comfortable vehicle and a vehicle that handles well. The Formula One teams, as I understand from talking to my friend, had a lot of discussions with the drivers about reducing the torsional rigidity of the monocoques in Formula One, because you're up around 60, 70,000 Newton meters per degree. Do you really need that level of stiffness? Could the vehicle still go as fast from a handling perspective with less stiffness and lower weight? And then, the Formula One teams, although they do have weight limits, they always try to get lower than those weight limits so they can ballast the car down low and effectively lower the center of gravity. He told me once that they actually used depleted uranium to ballast the vehicles down low, because they get the highest density out of uranium. It's expensive as heck, but they could really lower that center of gravity by using it. But anyway, so my point just being is that a full carbon fiber monocoque may be more stiffness than you really need on a road car, and that maybe something like a mid-spectrum design, when you have these big openings, and you keep the wind of the water out with something lightweight, like aluminum panels, or maybe some lightweight, low volume fraction fiberglass composite, or something that's inexpensive and lightweight that doesn't need to take a lot of load. It makes a lot of sense if you can go a little bit lower on the stiffness, which you can in a street car.
Awesome, thank you.
Yeah, you're welcome. The Audi A8, another interesting vehicle. I've talked about this one before. Clear, evident use of topology optimization. Great combination they've used of using aluminum extrusions and castings and pressed parts. Really neat car. What I have never really been able to figure out about the Audi A8 is it's not really significantly lighter than a Mercedes S-Class, which is made out of steel. And I think it must just have to do with the fatigue issue, that you have to put enough material back in order to get sufficient fatigue out of the structure, and that you lose a lot of your weight advantage. The Audi TT, a nice mixed material solution, aluminum for the closeout panels. That's kind of shown there in that sort of light green color, and then the primary structure was made of steel, high strength steel. Another one of my favorite cars here, the current BMW i3. I don't know if I talked about this last time, but the BMW i3 is a true milestone car. It is the first production car to have the primary structure made from carbon fiber, and the accomplishment, I think, is just extraordinary. I don't think people really realize what went into this car to do that. The i3 has not been a big seller in this country. People prefer Teslas because they have higher range. I can understand that. Elon Musk has been critical of the i3, but I'm not sure he really, I would love the opportunity to talk to him about the i3, let's say, and say, hey, this carbon fiber monocoque is really something amazing. The amazing thing about the i3 really is that not only did BMW figure out how to make the carbon fiber affordable, or close to affordable, but they set up the entire supply chain as well. So they worked with a company called SGL. It's a German company. And they set up acrylic pyrolyzation lines in Washington State, taking advantage of the Washington River to power the pyrolyzation lines in the plant. Okay, and so they, I'm not sure where they got the acrylic from, but they went from acrylic to the carbon fiber in this, so-called green washed or clean production pyrolyzation facility, and then they worked with resin suppliers and people who put the sizing on the fiber. So it's a little chemistry that goes on the outer diameter of the fiber, so it sticks to the epoxy properly. They put together that whole value chain, and that's really an accomplishment, because that's, I think, what got this vehicle close to being affordable. Now, I have friends who worked at BMW during the time this car was being developed, and they tell me that you can sort of smooth the numbers around a little bit, and you can convince yourself that they're not making any money in this car because of the carbon fiber. But yeah, they even got close, but they probably won't build another full carbon fiber car like this for a while. They've been, I remember when I was working at Mercedes in Germany in the materials research lab, there was a lot of discussion about BMW and the efforts that they were going through to develop carbon fiber, affordable carbon fiber. They had a whole facility set up in Regensburg, and there was all this discussion about, could we get in there to see what they were doing, and what if they're going to really figure this out and they're going to have inexpensive carbon fiber? Are they finally going to get down to that $5 per pound or something? And one of my managers actually somehow finagled a way to get into that facility in Regensburg. And he came back. He said, "Yeah, they're getting there, but don't worry about it. It's not going to be that cheap." So I guess in the mainstream, BMW's been able to sort of parlay this work into carbon fiber panels for roofs and some seat structures maybe and things like that. Control arms maybe for suspensions. They are using carbon fiber, I think, in the roof rail on the 7 Series is a weight saving but very safe structure to put in place of like a martensitic steel, which is what they'll often use on a roof header like that. Anyway, if you ever get a chance to go to a BMW dealership, it's worth it to go take a look at these things. If they have one in the showroom, you can very clearly see the fibers on the structure, on the roof and the door jambs. It's really interesting to see that this actually went into production, and they're really cheap. These things are depreciated like crazy because the range is poor. So you can buy them all day long for like $10,000 or $15,000, which is amazing. Anyway, okay, the new Corvette I included in this lecture, which I didn't last semester. The new Corvette is an absolute beautiful piece of work. Again, they've used a very interesting mixed material solution. They have sort of I think it's a carbon fiber floorboard. It's separated by balsa wood. So you have the skins of carbon fiber and then balsa wood in the center. That's what makes up the floorboards on the vehicle. They've used some incredible large aluminum castings in very creative ways at the 4 corners of the vehicle as suspension mounts. They've used extrusions. It's interesting. This vehicle is so cheap compared to a Ferrari that's probably not designed as well. It's really, really amazing. Great inspiration. Neat car. My personal feelings is it's gasoline powered, and I wonder how much longer. Like we're going to be driving gasoline powered cars, so maybe the milestone of an end of an era. Okay, and the final design I'd like to talk about is, I'll toot my own horn. Here's my concept. I think I mentioned this before about how to build a mid-spectrum vehicle for a passenger car. I published an article about this, or actually a book chapter about this in the book you can see on the right here. You can go look it up in the library. You might get a laugh out of reading it. But the concept being is that you make a very suspension oriented or centered design where the structure of the vehicle is really centered around where the suspension loads into the body structure. And I've used sort of a thumb. This isn't a real topology optimization. This is just my sort of artist rendition of a topology optimization result, but based on real results. But you see the K and Y structures in the roof and the back of the vehicle, and maybe someday I'll get to build one of these. Maybe just one off for fun. Okay, so I've gone through about 3 pages here of different body structures that are on existing vehicles. And does anyone have any questions on any of these, or want to bring up some cars maybe I missed that you think are interesting?
I have a quick question on the 2020 C7. If
Yep.
you go back to that on 129, so is the C? It was like kind of like, just for accuracy. I thought it was the C8 that was 2020, but I see that the yeah, I think so, but yeah, because I see that the drive shaft tunnel.
It's not a drive shaft tunnel. Let me double check.
Transmission.
Maybe I made a mistake.
That's not a drive shaft tunnel?
It's not. That is actually the primary load path. Hang on a second. You're right. I'm totally wrong. Thank you for catching that. How stupid.
Oh, okay. Actually, yeah, that makes sense because there's no room up front for an engine right now. Yeah, that's definitely
no, there's not. So you can probably figure out how this works, right? So the Lotus Elise has these big rocker panels, right, that are really difficult to climb in and out of the vehicle because they're so high. But if you go back to the slide I showed early on about how the stress changes in a tube under torsion as you go out, right? Remember I showed that the stress goes up with the radius to the 4th power, I think. So that means that in order to be the most structurally efficient, it makes a lot of sense to put a lot of structure out from the center axis of twisting, right? And so Lotus has these big, gigantic aluminum extrusions you see here, right? Kind of, it's just like a tube, right? You're also doing with a tube, a tube that has a big diameter and you twist it. is much stiffer than one that has a little diameter and you twist it, right? Because you're putting you're reducing the stress as you make the tube bigger, right? I showed that I think in lecture 2 or 3. Lotus has done the same thing here. They put these huge panels, but the problem with that, and I can attest to this since I've driven many Lotus Elises, is it's really difficult to get in and out of the vehicle, right? Especially getting out. You know, it's one thing just to sort of drop yourself down into it, but getting out of it can be quite difficult. In fact, with the Lotus Elise, when you bought the vehicle, they actually came with a video that showed you how to get into it, like how to put your feet, where to put your hands, and then lower yourself down in the car, and then how to get yourself out. And it's really hard to get out of it even then. But the mainstream Corvette customer, I think, is absolutely unwilling to do anything like that, to play those gymnastics. So Chevrolet, the Corvette people, took a different path. They decided to load up the center tunnel. So rather than having a lot of structure out here to take those torsional loads, they made a really, really strong tunnel, right? And that tunnel, I think, does the job. I think the car gets to pretty high torsional rigidity values, okay, but it comes at a weight penalty. And I guess that's just something they had to do. I mean, I'm sure they played some optimization games where they said, okay, how high can we really make these rocker panels before it gets really difficult to get in the vehicle? And I'm sure they did a calculation in torsional stiffness and, you know, what does the tunnel need to look like, and, you know, what can we live with on the rocker panels? But they did come with a compromise, and there was a weight penalty for that.
Yeah, I was gonna say, because that center line, I guess the channel, like, it's, I mean, obviously it's definitely not very far from the car's center line, and they also don't have any. It's like a convertible. I think it's, you know, the removable tops. You don't have any torsional rigidity up top as well, going from
exactly. I'm glad you caught that.
Yeah, so like it has to like be really beefed up, because I know I had a buddy who had like an older Mustang, and then his other friend had another convertible Mustang, and his convertible Mustang was like a few hundred pounds heavier because they had to beef up the chassis on like the lower parts because there's nothing up top.
Exactly. The Porsche Cayman and the Boxster, which are very similar vehicles, the same thing. They add a bunch of structure under the floor pan in order to get back some of the torsional rigidity, but they never get it back completely, and it's much heavier design, like you said, by a couple hundred pounds. That's exactly the definition of structural efficiency, right? I mean, the amount of mass they're using when we get a certain level of torsional stiffness goes down when you have an open design like that, right? Exactly, structural efficiency, exactly what I've been talking about. But customers like cars that have an open roof like that. People feel claustrophobic in like the what's that car? The Toyota, what do they call it? The 86, the 86, yeah, the Toyota 86.
Oh yeah, like the Subaru and the Scion one, that was all the same.
Right. Then the Subaru BRZ. So those little guys are incredibly torsionally rigid. I'm sure they're well over 30,000 Newton meters per degree. Incredible use of structure and efficiency. Lots of advanced high strength steel. Really a nice, clean, well done body structure for not that much money either, right? It's not a real expensive car, but I think people get claustrophobic in it. People love to have, you know, that open air feeling. You know, the Mazda Miata is the next closest thing, I guess. But
definitely.
Right. So people love that open roof, and that's where people like you know, Tad Euchter at General Motors, they make these open roofs like this, right? So they give up some weight in order to get that open air feeling. Personally, I'm not a big fan of it, but I understand it. You know, having seen the influence of marketing and the you know, true racing cars customers don't like. Let's face it, they're miserable to drive on the street. So
yeah.
Everybody talks about a race car for the street, but it really comes down to it. People don't really want them. Okay. Okay, so I don't want you guys to forget about fatigue. I brought it up here a couple times. I probably need to go back and figure out a way to characterize fatigue performance with regard to density and material. So like a specific fatigue performance. That's probably something I can put in for next semester. But I don't want you to forget about fatigue. There was a lesson that I learned early in my career. I was working at Chrysler, and the Jeep Grand Cherokee. They were developing one of the early Jeep Grand Cherokees. This was back in the early 90s, I think, or I'm sorry, late 90s, late 90s. That's right, it's late 90s. And they were looking at putting an aluminum suspension knuckle on the front suspension. This is the first time they'd ever done that on a Jeep vehicle. And back then, there was no separate Jeep line for, trail certified. Like every Jeep that came out of Chrysler had to be capable of driving off-road. So even this vehicle that had the aluminum suspension components. So they were trying to engineer a cast aluminum front knuckle. And again, the idea was reduce weight, right? They've been making these things out of cast iron for eons. Let's make one out of aluminum and see if we can save a couple pounds, especially because it's unsprung weight. And they kept having failures during fatigue testing. And they kept adding material back, redoing the fatigue test, add material back, keep doing the fatigue test. At the end of the day, they were actually heavier than the cast iron part because they'd had to put so much aluminum back in order to get sufficient fatigue properties out of it. So this is an interesting circumstance because the majority of Jeeps never go off-road, especially Grand Cherokees never go off-road. I mean, maybe Wranglers, a lot of them go off-road, but the Grand Cherokees, very few of them actually go off-road. Yet their design specification was that the car had to be off-roadable. So they had to create a design that had much more capability than any customer would ever, very few customers would ever appreciate. So it's kind of an interesting design compromise that they went through. But anyway, so I want you to be aware that different materials behave very differently in fatigue. Aluminum has what's called a fatigue limit. That means that there's always some combination of stress, okay, and number of cycles where you'll get a failure. The curve is always monotonically decreasing one way or another. Whether the slope isn't as steep or not, it's still always monotonically decreasing, which means there's some combination of cycles and stress where you're going to get a failure. That's a problem. Some other materials that do the same thing are brass. Magnesium has no fatigue limit. Steel and titanium are different in that they do have a fatigue limit. There is some theoretical level where you can go an infinite number of cycles, okay, and not have a failure. So there's some stress level below which, down here, below which, and the curve goes like this, if you're below this stress level, you can pretty much go forever and you'll never get a failure. I have a feeling that a lot of bicycle frames are actually in this regime because steel bicycle frames, unless they rust, tend to last a really long time. Things get more confusing when it comes to carbon fiber. Carbon fiber does fatigue, but it doesn't necessarily fatigue through classical methods. Now, fatigue is very much related to dislocation activity in metal. So remember we talked before about dislocations and what they were and how it was a missing column of atoms in the lattice, right? So you get a lot of dislocations that kind of move every time you hit a stress cycle, and eventually they kind of get closer and closer and closer until they kind of pile up on each other and make like a big void, okay? And then that void turns into a little crack, and that little crack starts to propagate until you get a fatigue failure. That's kind of how fatigue works. So steel apparently doesn't do that. Carbon fiber doesn't really deform by dislocation activity. But regardless, kind of the origin of fatigue is that you have some part that's under some stress. And if you look at it at some very small length scale, there's little voids, little pieces of material missing from the inside, deep inside the material. And those little parts where there's material missing, you get stress concentrations around the perimeters of those little tiny voids. And there's millions of voids in there, right? And because you've got these little stress concentrations very locally, at a very small length scale, the local stress can actually be much higher than the yield stress of the material. Even if the far field load is very low, and if you just take the simple equation of the force divided by the area, the stress is still really much lower than the fatigue limit, or much lower than what you should see in fatigue. Wherever that is on this curve here, you can still get that problem happening, right? Because locally, at a very local length scale, like I said, you've got these high stress concentrations, and the stresses are above the fatigue limit, and then or above the fatigue level, above the stress where the material should fail, and you get these little cracks that form. They begin to propagate towards each other. Then you got a big crack, and pretty much the whole thing falls apart. So, being material scientists and given the lectures I gave on designing materials for better performance, you might be asking the question, what is it about the structure of the material that leads to the property of having a fatigue limit, right? So we talked about processing, structure, properties, relationships, right? So what in the structure leads to not having a fatigue limit? And it turns out there's a thing called the stacking fault. Okay, so when you have these atomic planes, and the planes are, they line up in sort of these alternating sequences, up and down, stacked up and down, in millions and millions or billions of, maybe trillions of layers of atoms. There can be one of these things called stacking faults, where there's a missing column or something, or some missing void, missing atoms or something, and they don't quite stack up exactly right. And there's what's called a fault, a stacking fault. Okay, that stacking fault has energy associated with it. And depending if the material has a stacking fault or doesn't have a stacking fault can determine whether cracks propagate, are forced to propagate at grain boundaries or through grains. The materials where the stacking fault energy is low, like with nickel, steel, and titanium, the cracks are forced to propagate through a more difficult route. And because of that, you can have a fatigue limit. In materials that have a high stacking fault energy, like aluminum, like magnesium, like copper, this probably shouldn't say carbon fiber here because there are no faults there. Sorry. These materials are the cracks can go through much easier crack paths, and therefore they don't have a fatigue limit. They fail at some number of cycles of stress. They will always fail. I also want to mention that this is not absolute. Corrosion can assist in fatigue performance. And sometimes even materials that have a fatigue limit, like steel, if corroded, can fail regardless, even if they look to be below the fatigue limit. So just keep that in mind as you design structures, that if something's going to corrode, your fatigue performance can be dramatically decreased. Another thing I should mention here is that surface finish can have a really large impact on fatigue performance. So there's some beautiful graphs online you can look up that show fatigue performance of parts that are polished versus parts that are sanded versus parts that are bead blasted, and shows their performance in fatigue with these SN curves, stress cycle curves, as you see here. And materials that are, or structures that are highly polished oftentimes can do a lot better in fatigue. Another really important thing to know that I think very few engineers know, unfortunately, is that when you anodize aluminum, you can severely deteriorate the fatigue properties of aluminum. Okay, very interestingly, I've actually been involved with a couple consulting gigs now where I had customers call me and say, "Hey, this aluminum part's failing, and I don't know why." And then I would go in and take a look at it and say, "Oh, it's anodized." "Oh, really? Is that a problem?" "Mm-hmm, that's a problem." So anodization forms these little kind of hexagonal column structures on the surface of the aluminum, right? And they serve as stress concentrations. And because of that, when aluminum is anodized, you can oftentimes induce a fatigue failure at much lower stresses than would be consistent with a normal stress strain curve that you might find in the literature. Also, keep this in mind. A lot of engineers make this mistake. They anodize aluminum, then they load the parts in fatigue, and they have problems. The more intense the anodization, okay, the bigger the problem. There are some anodizations, I think with chromic acid, that don't have quite the problem that some of the other ones, let me say this again. Most aluminum parts today are anodized using sulfuric acid or phosphoric acid, okay? And these create these defects in the surface that lead to fatigue failure or can reduce fatigue margins. Long ago, they used to use chromic acid to anodize aluminum. And the chromic acid produces less of a disturbance at the surface, so the fatigue performance is not as degraded by as much. Okay, the problem is chromic acid is like seriously toxic, known carcinogenic, and except for the military, nobody's really allowed to use it. So keep that in mind. Like if you go into any anodization shop in Lawrence or whatever, or Redondo Beach somewhere, you walk in there and you ask someone to anodize a part. If you don't really carefully specify what type of anodization you want, they're going to use the sulfuric acid type, and you're going to get that fatigue deficit. Boeing developed a special kind of anodization which uses boric acid and sulfuric acid, and that's better. That doesn't do quite as good as the chromic, but it's much better than the pure sulfuric. So something to keep in mind. It's really very hard to find anodization shops that do that process that Boeing developed, but if you can, that's probably better to use. I know that a lot of bicycle parts are anodized, and I've never quite figured out what they use, but I'm hoping they use sulfuric, or maybe the parts are just lightly loaded enough that it doesn't really matter, and the fatigue is so far out in the future it doesn't really matter. Okay, any questions about, one more thing about fatigue. So I should mention that fatigue limits for steel and titanium scale with the ultimate tensile strength of the material. So that means if you have a steel that has 1,000 gigapascal ultimate tensile strength versus a steel that's got a 500 megapascal ultimate tensile strength, the 1 gigapascal or 1,000 megapascal material will actually have a better fatigue performance. You can kind of use that as a rule of thumb. It shifts the whole curve up. Aluminum, magnesium, brass, the same thing happens. Same thing happens. If you heat treat aluminum, or if you have one aluminum that's higher strength than another aluminum, you can expect the fatigue curve to be higher. It's a good, you should always pull up your SN curves, don't get me wrong, but it's sort of a good first pass at understanding what your fatigue performance might be out of a given material. And I should mention that if you start off with, for example, like a chrome steel or an alloy steel, and you get it in the annealed condition, so it's been heated and the dislocations have been diffused out of it, it's not that strong. Okay, you've got some fatigue limit that's here. If you then heat treat that part through a quench, a solution treat, quench, and temper, and the ultimate tensile strength goes up, the fatigue goes up with it. So fatigue will increase independent of how it got there, how the material got to be stronger, whether it was that way initially from the mill or whether you heat treated it. Fatigue properties will always go up. Okay, there was some question last semester and also this semester about crash energy absorption. And so I wanted to include these slides to talk a little bit about crush energy. Absorbing a front impact or rear impact in a production car is a very formidable challenge to do efficiently. It's something that becomes a real primary design focus at an auto manufacturer. How do we get this car to pass crash? How do we get the best crash performance we can out of it? This is something that's ended up in various, I don't know, insurance and government sources rate how vehicles do in crash. So crash is a very important topic. Mercedes, in their own research lab, actually has what's called a drop tower. So this thing is a drop tower for specifically for structures, for crash structures. And the tower is about 4 stories tall. And you take your specimen at the top, and at the bottom there's a target, and you literally just drop your cone or your crash structure, and you hit the target. There's all kinds of instrumentation that'll tell you how much energy was absorbed. And they've done all kinds of interesting materials. They've tested carbon fiber, they've tested aluminum, they've tested different grades of steel, and they've rated, you know, which of these materials absorbs the most energy per weight. So it's specifically energy absorption, so they can get the lightest, most energy absorption structure possible. The way to absorb the most energy in a crash is to cause as much volume of material to plastically deform as possible, because there's energy associated, right, with that plastic deformation. So the more bending and crumpling and volume crushing of material you can do, the more energy you're going to absorb. So independent of which material you have, that's a design requirement to see how much you can absorb, how much it absorbs the most material. In between the front bumper and the rail structure on a lot of vehicles, there's a separate little crash element. They're circled in red here. Because of aluminum's ability to absorb energy, a lot of times these structures are actually made out of aluminum, even if the rest of the vehicle is made out of steel. I've seen aluminum crush cones on Toyotas. I've seen them on Mercedes. I think I've seen them on Hondas. These 3 graphs kind of show my idea of energy absorption and crumpling. If you have a column that fails in Euler bucking, so you've got this column, it's under compressive load, and you're loading this thing up, and all of a sudden it just goes, the thing bends in half, like you see here. The energy absorbed is represented by the area under this curve. So the stress goes up, you get plastic deformation, and then you're still loading, so it continues to go down. The energy absorbed by this crash element is the area underneath this curve. If, on the other hand, you can get the material to fold a little bit, in some places forward towards the top, the crush distance graph is a little bit more tortuous. You get a little bit more up and down, some elongation. The energy absorbed by this element is represented by the area under this curve. That's more than this curve typically. This is better. The best thing is to get what's called stable collapse and regular folding, where you sort of have like an accordion. right? And you can deform as much volume of material as possible. In this instance, you get these high, high stress goes up, you hit yield, and then you keep folding, and you get these zigzag structures. And the area under this curve is much higher than something like this. And this is the type of structure that auto manufacturers strive for to design to absorb as much energy and an impact. Okay, and when you increase the yield strength of the material, this curve shifts up. Okay, there's been some really interesting sort of mechanics studies. Oh, Gabriel, got a question?
Yeah, quick question. So if you go back to the slide before, it seems like the structures are essentially the same. It's just extruded. I'm assuming aluminum, not sure what kind, but what sets these apart? Like, is it the material, or is there something within the structure that kind of like, like the beads that you mentioned, or kind of like folding zones that could allow that?
Yes. It's these. So this is all the same aluminum extrusion, but some of them have what's called a trip in them, an initiator,
Like a program.
It's like a little dimple in there that they'll put in order to initiate. But
okay,
there's been a lot of studies done on what cross sections produce this stable collapse, and there's a great paper by Budiansky that was published at Ford, like in the late 70s, where they did the mechanics. They did the structural mechanics to figure out what structures will lead to stable collapse. And they found that the more bends you have in the cross section, going from 4 in a square to maybe 1, 2, 3, 4, 5, 6 in a pentagon, and so on until you get to this really complicated structure here. The more energy you can absorb, the more likely you are to get that stable collapse mode. So this is a geometrical effect. I always forget, I think aluminum has some strain rate effect that makes it more energy absorbent than steel, and that's why they're used in crush cans. But really, does that answer your question, Gabriel? Does that make sense?
Yeah, definitely.
Okay. And a lot of times they'll put in little beads, like I said, little trips, initiation beads, like you see right here, in order to get that stable collapse. Sometimes they can't package a full hexagon or pentagon or octagon or this crazy shape. And so they'll put in these little trips. Usually that little gap between the engine and these rails is really hard to package in there. It's really hard. You're always trying to get the rails to move in order to get more turning radius on the wheels, so you can turn the wheels further. But you got to have a place for your engine, so that's pushing things out. So it's always there's a little tiny space between the wheels where the wheels turn to in that sort of longitudinal structure. Mercedes has done, like I said, these really interesting tests where they figured out what had the highest specific energy absorption. And their test showed that carbon fiber with thermoplastic, not a thermoset, but a thermoplastic, absorbs the most energy. And that's shown in this graph here. They actually, from what they learned here, do you guys remember there was the Mercedes SLR that came out in like mid-2000s? You remember that car?
That was awesome.
With that car, they actually took this information and they made the crush structures in the front. They braided carbon fiber cones, and then they infiltrated with the thermoplastic, and that was the crush structure on that vehicle. And yeah, it was really an amazing design. I remember that was actually designed in my department by Martin something. I can't remember his name, but I remember him working on that. It was really quite a nice piece. Probably cost more than most cars though. Okay, we're running out of time here, unfortunately. I guess I've been blabbing too much. I want to talk real quickly here about joints. If you have, a lot of times, almost always, you can't just have one continuous structure. Eventually, you're going to have to join tubes together, usually at 90 degrees, sometimes at one angle or another. But if you're sort of taking one tube and mounting it up against another tube in a way that's perpendicular to the central axis of the tube, you can kind of imagine that the tube really wasn't designed for that, and there's a good chance that when there's any type of load going from the perpendicular tube into the longitudinal tube, that you're going to get some local flexing there, right? And that leads to inefficiencies in the design. The most efficient design for a joint between two tubes, like this one here, or two hollow structural members, is to have these six shear walls. Okay, so you can count with me: 1, 2, 3, 4, 5, 6. Okay, this type of structure is very difficult to produce. It's the most efficient type of joint, but it's the most difficult to produce. And I remember when I was at Chrysler working on lightweight body concepts, I was trying to figure out how could we stamp a structure that looked like this? How could we take multiple sheets of metal, stamp them, and then put them together to form something that even approached this? And I think I mean, I didn't work on it full time, obviously. I kind of did it on my spare time, but I remember sitting there, with paper and rulers and trying to fold up structures to try to figure out how I could do this. I never came to a very good solution. 3D printing wasn't as popular back then as it is now, and I can see where 3D printing, you can clearly make a structure like this. Something to think about. This is the geometric side of joints, but we also talked about there's a material side of joints as well. Using bicycles as an example, I think I mentioned this before. Up until the state of the art for steel frames for a long time, up until about the 90s, was to make a lug using investment casting from steel, and then join the tubes into these lugs using a low temperature solder like a brass or silver. Another way to do this is to use a fillet braze, where you sort of artfully pile up molten brass around the tube. A lot of people do this. Well, not a lot of people. Some bicycle manufacturers, some like boutique high-end custom bicycle manufacturers do things like this. I got a bike that's done like this actually. I can see there's a lot of benefit in terms of reducing stress concentration because you've got these big radii. But the problem is that it's not very repeatable. And ultimately, I kind of wonder if it's kind of heavy because you got so much brass there. In fact, there might be so much brass here that it's actually heavier than using the lugs. And then TIG welding. TIG welding is a less expensive way to join tubes of a bicycle frame together. Okay, but because it's TIG welding, your heat affected zones are very pointy, but they're not very broad. So you get the stress concentration in a small area rather than a big one. If you're using a double butted tubing, which I mentioned before, it's where the wall thickness is thicker at the joint where the tubes are. If you're doing something like this and you have maybe material that even hardens when it gets hot and cools down in the air, you can get away with this and it can work. But it's certainly not a foolproof solution as far as I'm concerned from a structural efficiency perspective. I'm not going to say that like people who have bikes like this, like it's going to fail anytime imminently, but something to think about. That it's maybe not the most efficient design. Okay, so I wanted to say more about joining maybe next semester. Guys, any good questions about joint design? Gabriel, what's up? I think your hand's up. Maybe it's not a lower hand. Okay.
Oh, sorry. That was from before. I forgot to take it down.
Yeah, I think I'm supposed to lower it. I don't know. Anyway, does anyone have questions about this? No? Right. Okay, so here's the final slide. Just to stress what goes into a lightweight efficient design. In order to make the lightest, most efficient structures, again, you need geometry and you need materials. We first discussed the material side of this. The big goal is that you want to use materials that have a very high strength to density and stiffness to density ratios. As a good materials engineer, you'll say, how do I design a microstructure that gives me those high specific properties? As a mechanical engineer, when I was an undergraduate, I was taught to look up these values in a table and look for materials that had high strength to density ratios or stiffness to density ratios. As a material science graduate student, I got my face slapped basically for thinking that way and learned that no, you got to ask the question, how can I design a material that has higher strength and higher stiffness to density? We talked a lot about how to do that, the dislocation is the primary factor in a material's atomic structure that is affecting its yield strength. It is possible to control the deformation of material by restricting the movement of these dislocations through the atomic lattice. There's a number of ways to do that, including precipitation strengthening, solution strengthening, work hardening, making a composite, precipitation hardening. I mentioned that already. These are legitimate, useful, effective ways to design materials to increase the strength to stiffness ratio. However, stiffness to ratio is a little bit more complicated. The stiffness of a material is related to the atomic atom-to-atom interactions in the lattice. If you're using steel that's whatever, 97% steel or 90% steel, there's really not a lot you can do to change the stiffness. Stainless steel, which has up to like 20% chromium in it, There's a slight reduction in stiffness. It's not huge. It's a couple percentage. It's definitely not 20%. You can adjust stiffness a little bit that way. The only real way to increase the stiffness, the only real way to increase the stiffness of a metal or of a material is to form a composite. So things like carbon fiber. Carbon fibers themselves are incredibly stiff, incredibly stiff. You can't use them very effectively because they're like wet noodles, right? They're little narrow stringy things. But if you can find a way to transfer load from your input points, your boundary conditions of your structure into, sorry about the phone, guys, into those fibers, transfer the load from the matrix into those fibers, then you can find a way to take advantage of the stiffness of those fibers and build incredibly stiff structures. But the only thing to keep in mind is that those structures are then designed to be loaded in very specific directions. And once they're loaded outside those directions, you can get into a lot of trouble. So your bicycle frame that's made out of carbon fiber that only weighs a pound or less, a half a pound, it can be very stiff when you're riding it. You can take the loads as a bicycle rider would give it very effectively and make a very stiff structure. But if it gets loaded off axis, like if one of the tubes gets a normal load, it will fail very quickly and you'll lose your frame. So you have to be very careful with carbon fiber frames. They're beautiful things until they're treated the wrong way. Don't forget about fatigue. Joint design is really a lot to do with both geometry and materials. In regards to the materials, we talked about heat affected zones. Okay, Alan, this guy keeps trying to call me, sorry. In regards to materials and joints, like I said, heat affected zones, heat affected zones can dramatically reduce the effectiveness of your material. It can dramatically reduce this sigma y over density. So that's something to think about. Using adhesive can be very effective in making a lightweight joint because you don't need to put a lot of superfluous material in order to compensate for the heat affected zone. But the problem is that it's really hard to get the surface clean enough in order to make the joint safe. And I've had some personal experience with this. My advice to you is keep any type of silicone away from your bonding surface because it's impossible to get off and it will destroy your bond. Next, we talked about geometry. We talked about using geometry to make lightweight structures. We introduced the basic forms of loading, tensile, bending, shear, buckling. We talked about the stress distribution in those different cross sections under bending or torsion. We talked about how with something that's under tension or compression, the stress is constant across the cross section. But when you go into bending or torsion, the load can change to the square, the third power, or the fourth power as you go out from the center, the neutral axis of bending or torsion with those structures. You can use this to your advantage. You can make lightweight tubes that are subject to bending by going to a bigger diameter, but using a thinner wall. The bicycle industry has beautifully exploited this effect to reduce the weight of even structures that have a high density, like the steel structure. We took a body structure of a car. We broke it up into constituent members. And then we were able to take the constitutive laws of material loading and understand which tubes might be best made out of carbon fiber, which ones might be best made out of steel. Or can you save money making things out of paper or cardboard for all I care, as long as it's waterproof. All kinds of ways to reduce weight in a body structure by using these laws. We spent a lot of time talking about numerical optimization, that you can think of. You could break a structure down into design variables, the diameter of a tube, the density of an element in a finite element mesh, the thickness of a wall. You can take all these different design variables. You can have hundreds of thousands or millions of them, or maybe even billions someday. And you can create an unimaginable multidimensional hyperspace. And then using gradient optimization tools or genetic optimization tools, so-called heuristic tools, you can then search these multi-dimensional hyperspaces for places where the structure is the stiffest or the lightest. It's an incredible tool. These structural optimization tools, they've been used and are used every day in automotive companies and bicycle companies and probably boat companies and, I don't know, tennis racket and golf club companies to make lightweight, efficient structures where you very carefully understand the load paths, the most efficient load paths, and you use those load paths to create the lightest structure possible. And then finally, we talked about, again, we'll close again at joints. Joints are something you have to think about in terms of transferring stress from one structural element to another. And how do you efficiently do that so you get a stiff structure, so you're not losing everything you work for in other places into some normal load on a tube that just sort of collapses the side of the tube, and you don't have a stiff structure anymore. You wasted your time. Anyway, unfortunately, I've got a 10 o'clock meeting, so I got to run. But if you guys would like to have a discussion after this, later today or tomorrow, I can certainly make myself available for another conference call. Just shoot me an email. It's my email, I think you have it, but it's also, I have an MIT email address now too. It's dbaskin, so my first name Donald, the first initial, dbaskin1 at mit.edu. Okay, so like I said, if you want to talk, please let me know, okay? But I got to run. Thank you. Thanks for the semester, guys.
Have a good one.
Yeah, thank you. Goodbye.